This section is also extremely factual. These are the group 1 and the group 2A metals. Again, pull out your periodic table, take a look and see where they are. They are called the alkali metals, and we do not include hydrogen. Hydrogen is the oddball, best way to put it. They are very soft, and you can see the person cutting it with a knife. That is how soft these metals are. They have a very low density. Think of the lithium-ion battery. You know, it is in all of our devices. It is a very white light material. The atoms are the largest in each period, and I guess that's a fact. If you go from left to right, we're going to see smaller and smaller. All of the valence shell configurations are an NS1, and that single electron is easily lost because we go to that noble gas configuration. They will occur in nature as +1 ions, and again, the M+ has a noble gas configuration. If we were in class, I would be doing Breaking Bad. I would be doing the demo where we would have different ions in solution. Lithium ion would give us a red flame, sodium ion would give us a yellow flame, and potassium ion would give us a purplish flame. I'm missing doing those demos very, very much. And you guys would even go, oh, wow, even though there is YouTube. All right? So, where do these things occur? Well, they're in the ocean, they're in salt beds, and they are minerals. If you've ever been to a natural history museum and looked at the labels on rocks, you will see there are metals with a lot of the anions we talk about. If we want to get what we call the free metal, that's the metal in the zero oxidation state, it's often a complex series of steps, but we would melt the salt. What we would do is we would melt it. We would do electrolysis, and then we call it decomposition because actually it goes into 2 pieces. Now, we'll talk about this in chapter 20. In 1220, we'll talk all about electrochem and this process. But anyway, we make them by a redox process, but it's the opposite of what you're used to. +1 - 1 goes to form 2 zeros. So know that reactions can go in both directions. The other thing to tell you is that they do react with oxygen. You have to store them under oil. Another one of the demos that I would do in class was dropping the metals into water. On this slide, what I do is I show all the different oxidation states of the oxygen. With lithium, it forms an oxide. With sodium, it forms a peroxide. And with potassium, rubidium, and cesium, it forms superoxides. Again, these are facts. Here's a little, I always go to an aside. I was a Dow fellow in graduate school. I had many job offers at Dow Chemical. And if I had taken a job with them, I would have had a 6-month course in the chemistry of elements and things. I just didn't want to do that. I did not take that job. So essentially, these are all important facts, but it depends on your cup of tea, okay? Way to put it. So, as I said, they react with water. Lithium gives you what's called a moderate reaction. Sodium gives you a rapid reaction. And potassium, it gives you flames. So what they've tried to do here is to show it. There's our moderate reaction. I see a little bit of flame, our rapid reaction. But when I do potassium, we would have an aquarium and we would put water in it. We'd have water in it. We'd drop the potassium in it and it would just be giant flames. It was wonderful. They would never give me rubidium and cesium because they do explode. But notice, what it's going to form is a basic solution. Just like we said, metals react and form basic solutions. Here we have a metal forming a hydroxide, which is a basic solution. And it is redox. We went from a 0 to a +1. Actually, you can analyze so many reactions that you could actually figure out what is going on. What else is in this section? Well, the ones right next door to the alkaline are the alkaline earth metals. Know their name. I mean, that sometimes I've seen MCAT or PCAT things where there's paragraphs and all of these things are in here. And if you know it already, it's much easier to read the problem. These tend to be harder, they are more dense, and they are less reactive. They have a smaller size because they have an increased effective nuclear charge. You probably all know that they are an NS2. They form an M2 plus ion. When they lose their 2 electrons, they form a noble gas configuration. And they tend to pair with silicates, carbonates, and sulfates. No other ions are expected or observed at this point in life. So what do we have in our last slide? Just a little bit more about them. They react less vigorously with both oxygen and water, and magnesium and calcium, they are most abundant and important. There we have again the silicates, the carbonates, and the sulfates, and magnesium is found in the ocean. Now you do not have to know anything that I've written here. But what I wanted you to realize is in the real world, it is not as pretty as a textbook. If someone's trying to recover magnesium as a solid, they may take seashells, limestone, and heat it up to make calcium oxide and CO2. That calcium oxide is then dissolved in water to make calcium 2 plus and produces some OH minus. That OH minus is funneled in to react with some magnesium 2 plus to make magnesium hydroxide as a solid. That would be reacted with hydrochloric acid to make magnesium chloride as a solid, and then that would undergo electrolysis to produce the free magnesium metal. Now again, you do not have to know this, but I say it because I want you to see how much there is to chemistry. It's not the words we have in our textbook. In the real world, there's so much more that can happen. So what this really needed was a source of calcium carbonate, and that is limestone, that is seashells, they can be ground up. Then you had to have a source of magnesium 2 plus. Maybe it came from one of these rocks. I really do not know. But in order to get one path to form magnesium, this would be its actual route. Now, again, the most important things in this section is know your alkali metals, know your alkaline earth metals. Know their oxidation state, know their relative reactivity. It's a very short segment.